Good afternoon and welcome to this webinar brought to you by ESI Africa and DuPont Photovoltaic Solutions. My name is Claire Falkvane. I'm the Managing Editor for Sub-Saharan Publishing. Solar power in South Africa has rapidly progressed to become an almost 1 gigawatt industry, supported by government-driven subsidies and incentives. 4 years following its inception, the industry is starting to raise concerns about quality, reliability, and durability after a period of seemingly clear skies. The rush to get government-subsidized projects up and running at a very competitive price has in some cases resulted in compromises on the quality of the panels themselves. Cost per kilowatt peak has been all that mattered, rather than cost per kilowatt hour or the levelized cost of energy. In a recent survey, EPC and installer market survey conducted in Sub-Saharan Africa by ESI and sponsored by DuPont Photovoltaic Solutions, 80% of the respondents, the majority of whom are from South Africa, said they've experienced quality issues with their installation. 60% in 1 to 10 installations and 20% in 10 to 100 installations. The main quality issues included backsheet cracking and current leakage. Now, over 80% of the survey takers were small to mid-sized players, meaning 10 kilowatts or less than 1 megawatt, operating in the residential and commercial rooftop sector. When asked how important the following benefits are in the solar panel purchasing decision, 78% quoted warranties, 73% said that manufacturing quality assurance standards and reliable power output over lifetime was important. Asked to rank future improvement areas, 86% of the respondents quoted efficiency and 80% rated lifetime as the most important requirements for future solar installations. Now, during today's webinar, you'll be hearing from 2 industry experts in solar energy. Stefan Padliewski is the Regional Marketing Manager for Europe, Middle East and Africa at DuPont Photovoltaic Solutions, the world's leader in solar specialty materials, ranging from encapsulants, films for front sheets or back sheets, metallization plates, and structural component materials for frames, junction boxes, and inverter housings. The other presenter is Lawrence van Rensburg. He's the business field manager for renewable energy at TÜV Rhineland, the global leader in solar plant qualification, testing, and certification. Together, they're going to share insights based on extensive solar field surveys, best practices, and risk mitigation strategies to ensure your solar system powers longer and more reliably during its expected lifetime of 25 years or more. So without further ado, Stefan, I'll hand over to you.
Thank you, Claire. I hope you can see my presentation. So yeah, thank you for the kind introduction. And yes, so I will be covering for the next 20 minutes discussion around the criticality of materials in the context of the PV module reliability and durability in the field. And taking this opportunity to share some of the experience that we gain through a field survey program that we have initiated a couple of years ago. And we'll be sharing with you some couple of learnings with a particular discussion around the backsheet, as you rightly pointed out, Claire. Okay, just one word about DuPont. As you rightly say, DuPont has been operating in the PV industry for quite some time. In fact, if you are picking up a module in the field today, more than 50% of the module will contain some DuPont material. So DuPont operates upstream across the value chain, supporting primarily 3 product groups. The first is an activity around the metallization paste. The metallization paste is used on the cells with the 2 types of metallization: a front side silver paste that sits on the front side. So if you see a cell, you see some stripes on the front that would typically involve some silver paste. And then on the back, also some aluminum paste. So it's all about here efficiency optimizations. And it's also at DuPont very much an R&D intensive activities. You know, over the last 7 years, Just to give you an example, over than 110 products have been developed and introduced in this particular industry sector. So yes, it's all about efficiency. Efficiency is a very strong driver to help reduce the total system cost by making a better utilization of all the other materials. The second key activities for DuPont is around the fluoropolymers that has actually been used for many years in the PV industries. A fluoropolymers called TEDlar that is coming as a building block for making the backsheet. The backsheet is a protective layer sitting on the back side of the modules. It's the white film that you see that comes as a protective layers to protect not only the cell, but also to provide some electrical safety insulation to the module. So it actually plays a critical role for the module's integrities, and I will be covering more about some of the agings that we have weaknesses in the field with this particular type of this class of materials. The last but not the least activities is around an encapsulant material, a class of material that we call ionomers, some specialty material that have been designed. So it's a thermoplastic material. The encapsulant is the glue that holds together all the components within the modules. So the ionomers that we've designed can address certain issues such as the PIDs that are very much a subject discussed across the industry, but also designed for glass constructions. Also, as there are some increasing interest for this kind of packaging structures. So more than 50% of the module would include DuPont materials. So yes, so DuPont is obviously very present and have been present in this industry for over 30 years. From an upstream activities, we also want to see ourselves walking the talk and also supporting the development of the PV industry by allocating space across DuPont assets. DuPont own and operate many manufacturing facilities around the world. So we have initiated a program also to allocate some of the space to develop together with project developer partners, PV farms, onto DuPont soil. So as we speak now, we have 14 sites operating PV farms into it, and we have more projects coming in live. So in the picture, it's the latest one that we have launched. It's a system, it's a ground system that was commissioned last year on the DuPont facilities in France. Ground installation of 4.5 megawatts. So yes, ESI Africa has conducted, I think it was discussed just before my introductions, a survey directed to EPCs and installers all across the Sub-Saharan Africa region, aiming at assessing, the perception from that particular downstream communities on the PV modules. What are the qualities around the PV modules? What are the gaps as well, and the needs for future product development associated with PV modules? So I'm going to share with you only 2 slides associated with that. The first is, we ask a very simple question around quality issues experienced at the module level, and we're really surprised by the amount of issues experienced by all the respondents. So about 45% of the respondents experienced some quality issue at the module level, so which is quite a lot, considering the fact that the industry is pretty new across the Sub-Saharan regions. So among the quality issues surfaced up by the respondent, the first ones that came up were related to the backsheets. We heard issues related to the backsheet crackings, current leakage that can affect the performance of the inverter. So both are in fact related to each other. Some coloration variations as well, affecting either the cells or the surrounding packaging structures, the encapsulant and or the backsheet itself. Second category of issues surfaced up by the respondent involved cabling issues, ribbon corrosion that affect the cells themselves, and the third, some EVA delaminations from the glass mostly. So it's quite a high figures. So to the next questions, what will be the area of improvements for solar panels relevant to your installations? 86% of the respondents asked for improved efficiency, which doesn't really, it's not surprising, and efficiency, as I mentioned earlier, relates to not only to the power output, installation capacity, but it can also help reduce the total system cost. So that were the rationales surfaced by the respondents. The next one that came onto the radar horizons was a performance related to the lifetime, which relates to the previous chart with the experience around quality issue experience with the panels. So why lifetime is important? Well, because it relates to the ROI. It lowers the financial risk, obviously. It can help increase the power output of the system. And also there is some harsh environment related to the sandstone, frequent sandstone. It was mentioned a couple of times to other respondents. So, so one of the other aspects was around the flammability, the perception that flammability resistance was also an area for improvements to reduce the risk of fire, primarily for rooftop-associated installations. One of the industry imperatives, and that relates now all of the discussion around quality, is to compete on the LCOE basis, the levelized cost of energy versus other source of energies. It's all about producing electricity at the end of the day, so photovoltaic, like any other source of energy, has to be competitive. So what drives the LCOE, what comes on the top of the equation, the top line of the equation, what comes in the system cost, and that's something that is very well understood. So system cost includes the module cost, the balance of system costs, the operational and maintenance costs, and also obviously the cost of financing. So this is an area where the industry has put a lot of emphasis over the last years. But what is not so much visible, and what hasn't been talked so much, is what is happening on the bottom side of the equations here. And it's all about the power output over the actual system lifetime. So that takes into account the annual degradation of all the components and the PV module in particular, as well as the component failure that can affect the reliability of the system. Everything here can dramatically affect the financial and affect the LCOE and the return on your investments. So this is an area where, as an industry, we need to spend a lot of time, as it is usually assumed that a system will perform very well over the lifetime, the expected lifetime, which is 25 years today. But in reality, the actual lifetime may be much shorter, and that can actually strongly impact the financials. So one of the issue as an industry you are facing is the fact that the current quality standards we're using are derived from the IEC certification, which involves a set of accelerated testing protocol conducted mostly on a parallel basis. So there are some, and the IEC testing has been designed primarily to detect infant mortality issues, not so much to predict the long-term performance of a system operating under a given climatic environment. So that's really one of the major issues we are facing as an industry. So in fact, all the system you are using and the modules you are using are all IEC certified, but still you will find a subset of the system that will actually fail in the field. So I'm just highlighting here some key differences. The first is the fact that a module over its lifetime will endure a lot of UV radiations, far more than what is actually used under the IEC conditioning protocols. So under IEC testing, you typically flash the modules from the front side, so the back side of the module doesn't see at all any irradiations from the UVs. So there is no aging at the backsheet level that will occur from that perspective. Now in reality, if you put a module, say on the ground installation modules on the top of a sandy floor, the floor actually will reflect a big chunk of the light, the incoming light, within what we call the albedo. 12% of it will be reflected back on the backside of the module, and that amount of UV radiation can actually degrade the polymer themselves. And that's actually what has been seen in the field, which is not seen at all under the IEC certification. And of course, the higher the irradiation intensities under desert condition, the worse the situation gets. Building upon it, there is also, the IEC does not really differentiate the stressing protocol by application. So here I'm picking up the case of a rooftop examples. It's actually a fast-growing industry, segment in South Africa. So rooftop is actually a quite stressful environment if you think that modules that apply onto a rooftop have usually left with a very limited air gap on the backside. So there is a very bad circulation of air. And so you build up heat, and as a result, the modules operate under higher temperature, and this is what is actually explained in this particular chart. So in module on the rooftop, pitch rooftop can actually operate up to 15 to 25 degrees with temperature higher than 25 degrees versus a ground installation. So higher temperature means higher stress. It also means higher thermal cycling and fatigue. Which can also accelerate the degradation of the system. So you have to be very careful how to pick and choose all the subcomponents from the thermal resistivity standpoints. Okay, so from the IEC, in fact, as a result of that, a couple of years ago, we have, DuPont has initiated a program aiming at surveying modules deployed in a field and to pinpoint the visual degradations that could be observed at the module level. Now, the degradation we're referring to, we were interested in, were only visual change versus the nominal configurations. So it doesn't necessarily mean that a defect that we picked up would be a functional defect. But a visual sign, a visual change means something. If you have a polymers turning yellow, it means that it's actually, its properties are changing. So it's basically a precursor, a sign that something is happening, and that may affect the overall performance of the modules. So we conducted a survey. Our team, a technical team, has conducted a global survey. In fact, it's continuing doing so. There is a great deal of learning from the field. So surveyed so far 60 systems across the globe, pretty much, in North America, in Europe, as well as in Asia Pacific. And one of the key things we found was that over 40% of the panel survey displayed some level of visual degradations. 60% of it were related to the cells. So cells type of degradation would include the snail trail, the way we looked at it, hotspots, some corrosion as well that would affect the bus bar of the cells. Now the next one would affect the backsheet itself, and I will be spending a little bit more time on that particular one. The backsheet accounts for 22% of the defect observed, and the third would be the encapsulant itself, some yellowing in particular, or delamination from the front side glass. Now, one thing interesting about the backsheet, we picked up, we were primarily interested to understand what kind of material would age and what would be the statistic associated with that. So we found out that there is a good deal of sensitivity with the type of backsheet used and the kind of problem actually seen. So all materials do not behave the same. So we found a great deal of issues with a certain type of backsheets, PVDF based, and that's the outer layers. The backsheet is a composite material, so we only could pick up the outer layers chemistries with a special tool that we're using on the farm while we are surveying the systems to pick up the outer layers. So the PVDF-based backsheet accounted for the majority of some of the issues we observed, followed by the PET-based, and then the last was the PVDF, a TEDLAR-based backsheet. Only very few defects observed with that. So we found a great deal of sensitivity with the material used. Now, drilling into more details throughout our field studies, we looked more carefully at the backsheet degradation. We categorized the farm that we surveyed by the type of backsheet used by module manufacturers, with a PVF-Tedlar base, with PVDF, with PET, and with FEVE as well. There are other type of backsheet as well that we didn't count it here. Those were the majority of those we actually found in the field. So it was like a blind survey. We didn't know what we would find. So we had our special equipment to tell us what actually was used. So you see that the average system age was also varying a great deal. Tedlar has been used for many years, so it was not surprising that the average age of the system we surveyed were older than all the other ones. Now, one thing was striking, looking at the percentage of defects pinpointed at the backsheet level. I mean, you see a great deal of variation depending upon what you are using. So if you pick up PVDF, we found that 43% of the panel survey displayed some visual sign of degradations. The most common one for PVDF was the front side yellowing, and I'm going to show you a couple of pictures so that you can understand what I'm talking about, but also some cracking associated with that. The PET also was the second one, coming with the highest rate of defects, with also front and backside yellowing, as well as delamination and crackings. So here you see the material makes a very big difference with the outcome and the kind of degradations that can occur at that level. Now I'm showing you a couple of pictures. I don't want to scare everybody. It's just to show what I'm talking about. This is typically what we call a backside yellowing. This is typically what we see with polyester. Polyester are inherently not robust to UV, so they intend to age. So UV would basically, UV combined with the thermal stress would degrade and change the coloration of the backsheet. So the change of coloration typically tells you something about the property of the polymers. Polymers becomes more brittle. So it's not very good for polymer scientists when you see something like that. So here is an example of two panels. On the right-hand side, you have a PET-based backsheet that displays some yellowing, and on the right-hand side, you have a PVF-based backsheets. Both panels were displayed at the same location, involving the same manufacturers. So that variabilities, the manufacturing variability was out. So here you see the two different outcomes after 10 years of operation in the field. This is a much more severe issues, a cracking, what we call a deep cracking, according to our nomenclature. So you can see the rebound on the left-hand side pictures. The rebound actually can operate at 1,000 volts, so that represented a serious issues. When you see that, you basically have to replace the panel. You don't have any electrical insulation on the backside of the modules. You can also generate some current leakage. So in fact, the operation of your module may be very difficult at that point of time. So this is a serious concern when you see something like that. That's another type of defect, also very common with a certain type of backsheets, the PVDF. Actually, this yellowing is what we call a front side yellowing at the backsheet level. It's a tie layer. I mentioned that backsheets are composite material. It's the inner layers of the backsheet that typically includes some chemistry that degrades under UV radiation, the UV coming from the top side of the panel. So the yellowing affect actually the adhesion of the backsheet. So the risk here is delamination and again the loss of the loss of electrical protection at your module level. So this is a very common issue that we've experienced in the field. You probably have seen that as well. Now, I wanted to talk very briefly about the diffuse hotspot. When you shade the cell, it cannot generate a peak currents, an optimal peak currents. And cells are mounted in series within the modules. So when a cell gets shaded, it would act as a resistor. So the other cells would keep pushing a higher currents than the one that this particular cell can absorb. So acting as a resistor means that the cells affected by the shade will start generating heat, resulting into a higher temperature. So this is a fairly common situation, and the reason I'm surfacing up this particular issue is because it relates very much with the dust. In an area where we see a lot of dusting, the situation can be very common. Now, modules are typically designed with the bypass diodes to shortcut the situation. This is typically what is happening on the top left of the situation. The shaded area actually is getting cooler because the current doesn't get through. The bypass diode built in within the junction box bypass it, so the cell doesn't have the opportunity to heat up. Now, in many situations, in fact, a group in Japan has conducted a couple of years ago studies to assess the performance of the bypass diode. They found that over 45% of those diodes would not function properly under such situations. So when the cell starts heating up, the temperature can exceed easily 100 degrees centigrade. It can really boil water onto your panel, and this is the situation represented on the right-hand side of the picture. Now, there are some risks associated with a high operating temperature. The risk when the bypass diode is not functioning properly is, a higher temperature cells can degrade the EVA itself. It can brown, as it is shown on the top left pictures. It can also degrade the backsheet on the backside, and that's actually more serious. You can generate crackings if you don't properly choose the backsheet itself, or a backsheet too sensitive to thermal excursions. So it can crack or it can delaminate. So here it's a risk around losing the electrical protections. Now, a functioning bypass diode can also generate issues at the junction box level as it generates heat. So you can also melt the junction box. Now, to mitigate the risk at the backsheet level, we typically recommend using backsheet with the highest softening point temperature for the inner layers. So we typically recommend the use of a backsheet construction that we call a TPT to minimize that risk. Now, just to sum up, you have to really think for a PV system. If you are a project developer or an EPC, you are willing to think in terms of LCOE, on the cost on a kilowatt hour basis, rather than the cost, strictly on the cost on a watt peak basis. Reliability and durability are critical. So the power output over the actual system lifetime is critical. So you have bear in mind plug-in qualities while developing your own system to ensure that they will operate reliably and durably over the expected lifetime. A couple of other messages. The IC certification is not meant to predict the long-term performance of the panels. You have to remember that the backsheets are designed to provide the electrical safety protections as well as maximizing the cell power output over the expected lifetime. Panel mounted on the ground will endure a high level of UV radiations, through albedos. On the rooftop, they will endure very high thermal stress. So you have to very much to be careful while selecting the components. Now, we recommend, in fact, for the two segments, so for the Sub-Saharan Africa, considering the high thermal stress environment, the UV stress environment, we typically recommend the use of a TPT-based backsheet to minimize the risks. And this is confirmed by the 40 years track record in the field. Now, to leave you with a positive pictures, we talk a lot about war stories here. A PV system can be very reliable. In fact, there are examples out there of systems that have been operating for more than 30 years. So you can be safe. This is the right industry to be, but you have to be very careful in qualities. Building up qualities right up front while developing project is key to make it happen, and for the sustainability of our own business. Having said that, thank you.
Stefan, thank you very much for that very informative presentation. Lawrence, I'd like to hand over to you now.
Thank you. TÜV is a global market leader in testing and certification of solar products and power plant qualification. We have more than 30 years of experience in PV, and we have inspected more than 12 gigawatt of PV plants worldwide. We ran a study on the plants we inspected from 2014 to the first quarter of this year regarding the cause of defects and performance losses found in PV power plants. The source of the problems found in the plants is indicated as follows. 55% was related to installation faults, and 25% related to documentation and planning faults, and 9% regarding product defects, and the rest you can see there. On the plants we inspected, 30% of them showed serious defects, and 50% of these defects were caused by installation errors. As can be seen, 43% of the failures were on modules, and 21% cabling, and 18% connection and distribution boxes, and the rest can be seen as well. Therefore, inspection and maintenance of your PV system is a necessity. Here are some examples of serious defects which would require immediate attention if found in your PV plant. Connection and distribution boxes, where we had missing covers. Related to modules, we had glass breakage, burnt junction boxes. When it comes to inverter out of operation. Mounting structure, risk of mechanical damage. With cabling, damaged cables, connectors burned down. And then transformer stations, panic lock blocked. We performed a comparative study in order to determine if there would be a difference in module performance with and without third-party quality measures. The graph on the left-hand side indicates the deviation on measured performance related to the nominal performance stated on the modules. These modules were selected from small-scale installations where there was no third-party involvement. As you can see, 25% of the modules had a 2% lower performance than stated on the modules, and some up to 7% lower. The graph on the right also shows the deviation in performance, but the modules tested were from projects where the manufacturer knew that the modules would be tested by a third party and proper quality assurance protocols were followed. As we can see in this graph, it shows quite a different picture than the previous one. As we can see, 25% of the modules had a 2% higher performance and some up to 5% higher. Therefore, third-party performance measurements are a necessity in large-scale projects. Also to note, some law disputes we have helped with require a high level of measurement precision and accuracy. So how do you get your projects bankable and reduce project risks? Most important is to have technical due diligence performed. Thereafter, financial due diligence, and finally legal and tax due diligence. For the technical due diligence, factory and production audit should be taken place, product quality check regarding your modules and your inverters, PV plant design, PV power plant approval, PV plant inspection regarding safety and performance, provisional acceptance tests, final acceptance tests, and then the review of contracts focused on the technical parts. When it comes to selecting a manufacturer for sourcing PV components, benchmarking of production quality is key. The process for scoring the manufacturers are as follows. A factory audit is performed where we evaluate the quality management system, protocols, production processes, and methodology and quality control measures. Samples are also selected for testing to benchmark the components' quality related to international norms. Once you are happy with the PV component manufacturer, third-party quality control should be in place, where factory production inspections and audits are performed on batches for your PV plant. Also, pre-shipment or post-shipment tests should be performed on samples picked before and after shipment. As can be seen, there are 3 phases to be followed and the related activities which I have explained. You can normally decide what testing regimes should be followed, but our recommendation is to have either a quick performance check done, which includes visual inspection, performance measurement to STC and electroluminescence pictures, or to include the quality benchmarking tests to be performed regarding gel content test, peel test, light-induced degradation, PID and wet leakage current tests. For the sourcing phase, we would suggest highly that the quality benchmark tests are followed, and that before shipment a smaller percentage. During project planning, independent site evaluations and yield predictions should be performed in order to determine meteorological data for your energy yield, component and installation parameters, and loss of revenue factors. Then the assessment of the facility concept and the components, where we were looking at the compliance of planned components, necessary approvals, system specification and drawings, and risk analysis. During the construction, on-site inspection should be performed in order to detect the following deficiencies in advance regarding wiring, ground fault and short circuit safety, general construction and PV module orientation, and lighting and plant protection. Another quality measure for PV plants is to have a reference string built on your plant where you can detect and monitor if there is any degradation present in the modules installed. An initial performance check is done on the modules at a lab in order to measure the initial conditions and performance of the modules. After testing they are installed in the reference strings. During plant operation, you are then able to monitor and analyze data from the reference string, and you can compare with the rest of the plant's analysis. Before the end of your warranty, or in case of claims, the modules from the reference string are tested once again in a lab in order to compare with the initial measurements and to detect if there are any degradation present in the plant. Before the plant is commissioned, acceptance testing should be performed where visual inspection is done on the installation quality. Performance measurements and installation measurements are taken to determine if the electrical connection is done correctly and the relevant expected performance from the strings are correct. Corrosion coating tests are performed on the mounting structures, and infrared measurements should be taken to find hotspots on the modules and electrical connections. When we look at small-scale PV, the biggest risk is fire. From a study performed in Europe, we found that in the past 5 years, 180 heat and fire damages was caused by PV systems. In 65 instances, buildings were damaged, and 49 instances for PV systems. The cause of the errors was mainly from modules, inverters, and AC distribution, as can be seen. At least 50% of all the errors was caused due to bad installation. From the commercial industry, it's very difficult to evaluate the competence of PV installers. One way is to have a certification scheme in order to certify and qualify installers. What would be evaluated is how the installer advises the end user and the on-site advice from his personnel, the content and terms of his quotations. The quality of some of these installations are evaluated almost in the same way as for PV plants, and the qualifications of the installers are then evaluated. The startup and safety instructions are evaluated, plant documentation are looked at, suitability of used materials and components, the installer's customer support, the monitoring and securing of plant operation, customer satisfaction surveys, and examination of individual installed plants of the installer. In order for installers to mitigate risk and premature system failure, we would suggest the following measures to be taken by rooftop installers. Only have modules installed that are certified to at least IEC 61215 and IEC 61730. Module quality control should be taken by having a sample of your ordered batches tested or in-process inspection performed at the manufacturer. Proper planning to be followed, looking at shading analysis, proper designing aspects using proven software, and taking the type of roof and area conditions into effect. Also to look at adequate space planning in case of fire. To send your technicians for training regarding quality of PV installations, to use compatible components and to use only components that meet PV specifications. Perform a safety inspection by looking at critical components with an infrared camera. To perform a visual inspection of the installation in comparison to the design and best international practice. And to ensure quality assurance of your installations, to have a third-party, by having third-party audits and to be certified as a competent installer. Thank you for your attention.
Hello, thank you. Sorry about that. We had a little bit of a technical challenge on this side. We've had a couple of questions that have come through, and I wanted to address the first one, Stefan, if I could, to you. And it's from Elijah, who wants to know, when you say modules mounted in close contact to rooftops are more exposed to the highest operating temperature, how do you justify biface PV efficiency over one-sided? In which case, when the biface is not so close to the rooftop, it tends to generate more power owing to the rebounds from the rooftop to the second side of the cell. Are you able to give that, some insight into that?
Sure. Well, in principle, the bifacial technology is mostly directed for, off-soil application where you need some reflections from the back. So whether you recommend using such a technology platform when the module is mounted close to the rooftop, in principle, it doesn't fit with this particular application. And it's also a glass structures in most cases. So this technology is primarily directed for ground installations, where you have a relatively high albedos. High albedos, the highest albedos surfaces would include typically sand. The 12% I mentioned earlier, albedo would be for the sand surface. So you would utilize these particular technologies for ground installation and wherever you have some highly reflective soil. Now, obviously, a rooftop is not the case unless you go for flat rooftop applications where you can actually leave some gap versus the surface of the rooftop. It's certainly not the best application you can consider. The second issue you face with the glass structures typically used for bifacial technology is the weight issue. I mean, glass are typically heavier than a glass polymer or backsheet-based structures. So rooftop, in many cases, are weight sensitive. So it's pretty hard to utilize this particular technology platform for rooftop application. So I'm surprised that that it came as a segment, as it is mostly directed for ground installation. For rooftop, you would probably better use a conventional glass backsheet structures as weight matters typically. So you would go for the lightest platform, so glass backsheets. And the most durable, as I mentioned earlier, would include the backsheet with the highest thermal resistance, in particular the inner layers resistance, such as the TPT. So to answer the question, I mean, you would not gain much having a bifacial on the rooftop in a situation where the module is mounted and very closely to the surface of the roof. Yeah.
Fantastic. Thank you so much. One of the questions that has come up quite a lot in some of the questions that are coming through, and this is more just for all of you attending, the presentation will be available and you will be getting a link to a copy of this webinar and to the presentations a little bit later tonight. Now, I have another question here from Chris, who wants to know, how do you compare the degradation of thin film versus C-SI technology in Southern African installations to date? Stefan, I think that this is one for you as well.
Well, I mean, we have a survey. Our team has surveyed many systems. They primarily surveyed crystalline silicon-based modules, so very little experience with the aging of thin film, whether it's amorphous silicon or CATL or SIGS technologies. There are some data here and there. And some concern that have been pinpointed in an installation, as we are aware, somewhere in the Middle East, with a thin film system involving glass solution. Now, the issue was not so much about the power degradation, but it was around the glass breakage and some of the issues associated with the mounting structures. Now, maybe TÜV has some additional experience with thin film and may want to provide some additional comments.
Yes, there's been one or two thin film projects that have had some discolorization on the modules, but we're still in consultation and we're still doing the tests on that, so can't give too much information regarding that yet. There's not much information regarding thin film yet for South Africa.
Thank you, Lawrence and Stefan. So another question that comes from Edwin is, what will the specific risks for Sub-Saharan or for Sub-Saharan Africa be in terms of ground PV or rooftop? Stefan, would you like to elaborate on that, please?
Yeah, I mean, the stress environment, the way we look at it, would be significantly higher than in most other regions. Certainly compared to temperate climatic environments, such as what we find in Europe, for instance, or even most part of North America and Asia, as a matter of fact. So we do expect, fast degradation if you don't pay attention to the component themselves. That's why we want to bring these issues on the forefront of the industries, that you are really to carefully select not only the components, but the subcomponent themselves and the material used by the manufacturers, and to select them on the basis of the endurance versus thermal stresses, because you typically operate a system at a higher temperature. And also because the UV radiation is, as a result, is also higher. So you have to make sure that you build in UV resistance within the polymers that you are using, which is why I brought up the discussion around the backsheet, because it's really the protective layers that do see a lot of UV irradiation. So make sure that you utilize materials that are proof with respect to the UV radiations. And the last but not the least is the sand abrasions and the sanding issue, the dusting issue that can relate to the hotspot, the diffuse hotspot discussion that I brought up very briefly. The risk here with the diffuse hotspot is it is in principle the dusting can generate the hotspots, the diffuse hotspot, and this is a reversible process if you clean up your panel typically. And if you don't, then you will generate some heat, and you will have a higher temperature, operating temperature at the cell affected by the hotspot that can accelerate the degradation. That relates again to the need to select materials, surrounding materials that are the most resistant from the thermal stress standpoint. So yeah, those would be the risks associated. So higher risk of dusting and hence a hotspot, and generally speaking, a higher operating temperature and a higher UV radiations. So yes, all these factors can accelerate the defect. In fact, we're very interested. Our team is very interested in 1 or 2 years to conduct survey in your area, because now the system are getting old enough to start seeing, and it looks like, according to the respondent of the survey, that you do start seeing problem or issue with the panel. So there is a great deal of learnings for all of us to start developing some best practices to minimize the risk for future project development.
I think that is going to be a very telling survey and some very telling research once you've had the opportunity to have a look at how these systems are actually performing in the field, as you say, after a little bit of time. Lawrence, one of the things that I was wondering is, would you be able to clarify the data on the fires in slide 11, as this related to Germany only? Do you have any other information that is outside of that area?
No, you're right, it's only related to Germany, not only Germany, it's some countries in Europe as well. So it was Italy, it was not only Germany, and I think Spain was also included.
Okay, thank you very much. Then we've got another question from Elijah, who wants to know, is it possible to advise on if the PV is installed near the roof, what is the possible distance of the installation in order to take advantage of biphased PV benefits? Stefan, for you?
Well, I think this is with the data. Actually, I think it would be good to look at and to engage the manufacturers, the module manufacturers, because they typically conduct the testing. In fact, one of the issues the industry is facing is the lack of agreements or common agreement on how we should test the performance of these panels, because in reality, the power output of your module strongly depends on what is happening on the backside, the surface used. So how do you provide a rating for a module is not a generally accepted process among manufacturers. So for a particular project, you really have to look carefully, what would be the minimum distance at which you would not lose too much reflection at the back. I don't have already the answer to that, but I would certainly approach the module manufacturer, to have some guidance, because they may have carried some testing themselves to evaluate the actual power output, various mounting configurations. But typically, it's designed for ground installation. I know that most manufacturers are positioning this particular technology platform for ground installation, where your module is way away from the ground, and where you do see a lot of albedo and reflection from the ground.
Great. Thank you. Elijah, I hope that answers your question. Lawrence, one question that has come in is, how long does the testing and certification process take?
For what? For rooftop or for the normal PV plants?
It hasn't been specified, but could you maybe give an idea on both?
Okay. For PV plants, it depends normally on the size of the plant. So if we're looking at a quick performance check where we just look at the testing for visual performance, if we take a, let's say, 80 megawatt plant, that's the normal size that we have in South Africa. You're looking to about, we're looking at about a month to a month and a half for testing. But like I said, it's dependent on the size of the plant. Then when it comes to rooftop installations, if we want to certify the installer, that's dependent on the installer. If he's ready for an audit, we perform an audit, that can normally take, that can also take up to a month normally to process. The duration of the audit will most probably take depends on the size of the installer, so it might take 2 to 3 days, and then to review all the documents and for the certification, let's say about a month.
So this is not necessarily a very long, drawn-out process.
No, but like I said, it depends on the size of a plant. If you're looking at PV plants, it's also dependent on how busy our lab is. It's very difficult to say. Also, it depends on what the technology is. If it's thin film and it's quite a big module, it might take longer. PID, for instance, if you're looking at PID for silicon, your PID normally takes also about a month to a month and a half for the PID test.
Okay. How big is the risk of fire on PV cells, based on the information that you provided in slide 11?
Well, if we can look at the data that we've had from a study that we did, I mean, 20% was related to your PV modules. Regarding cells, the fire wasn't related to the cells, it was more related to the junction box on the module.
So really the important thing for people to be aware of here is that it is not necessarily the technology that has quality issues, but of course the installation can make a big difference in terms of how it goes forward.
Exactly.
Okay. Okay, so Elijah has just come back to say that this has been very educative, and that he would obviously like to have a chat to you guys about some work that they are doing. So Elijah, thank you for that. I have a feeling that somebody from DuPont will be in touch with you fairly soon. Ladies and gentlemen, we have unfortunately come to the end of our time here for the question and answer session. And Stefan, I just wanted to find out from you, is there anything else that you would like to mention before we close off this afternoon?
No, it was great, very good, and thank you for the opportunity, to bring this issue up to the attention of this industry. It's emerging across the region, so it's really very important for all of us to do the right things for the sustainability of this industry. We're all sitting together with all across the value chain, so we're all connected, obviously. So we have to be very careful and bring this to our attention, this notion around qualities, and make sure that the system will operate reliably and durably over the lifetime. So everything is important. Obviously, we pitched something around material. It starts from the material, but also at the module level, you have to do the right things for a module manufacturer to deliver a quality product. But certainly also at the designing and installation stage, it's equally important, as things can go wrong all across the value chain. So it's very important we keep learning from the field and keep sharing to all of us the best practices to minimize the risk and to ensure a good and sustainable industries, photovoltaic industries. That's it. No, thanks a lot for arranging this discussion.
Absolutely. I guess there is something to be said in that old adage about a chain is only as strong as its weakest link, and this has definitely been borne out by the fact that no matter how brilliant the product is, if there is a weakness somewhere else along that chain, it's going to show, and vice versa. So I guess it's not just about quality of product, but quality of installation as well.
Absolutely.
Lawrence, before we end off, is there anything else that you would like to say? We've got a minute before our time is up.
Yes, PV plants, related to PV plants, project developers and investors should make sure that they don't only give carte blanche to the EPCs to select a third party to do the performance measurements. They should basically select them themselves, because what we've also seen in the industry is that Some of them just get normal electricians to do the performance measurements on site, to do the installation, quality checks, and they don't know much about PV installations, but more related to electrical installations. Unfortunately, you need some background regarding PV and not only electrical. Regarding rooftop, like I've suggested before, TÜV is available to provide installer certification for the industry, and that's something that they should think of.
Absolutely. So developers, the responsibility for ensuring that your team is the best that you can get, unfortunately, still tends to lie with you. But of course, that's always to your benefit. So I would like to say thank you to both Stefan and Lawrence for taking the time this afternoon. We've had some really interesting questions, I think fairly technical questions, which has been really great. It obviously shows that the quality of the audience that we have with us this afternoon are people that are really interested in a very real and technical way on what's happening, and especially around quality. So thank you to everybody for your participation. To Stefan and Lawrence, thank you so much. And to DuPont Photovoltaic, thank you very much for helping us put this together and presenting this. Ladies and gentlemen, you will receive copies of the presentations, as I said, later on this evening. And from me, Claire Falkvane, to all of you, thank you very much. Have a great evening.